Hello. Good morning to one and all present over here. I welcome you all back again to the day 4 of Faculty Development Program in Artificial Intelligence and Machine Learning. We are pleased to welcome again Dr. Prasenjit, Assistant Professor in the Department of Computer Science at National Institute of Technology, Rourkela. Sir is well known for his strong contribution in the areas of artificial intelligence, machine learning, deep learning, IoT, along with several high-quality research publications in reputed international journals. It is an honor to have him with us for another insightful session. May I kindly request Sir to take this stage and inspire us with another exciting session. Sir, please.
Thank you for this warm welcome. So in this lecture I would like to talk about the support vector machine, SVM, which is a statistical machine learning technique. So in this session I will start my discussion with VP theory or VP dimension, VC dimension I should say. So Vapnik-Sermonenki's theory. Then I will talk about structural risk minimization and how SVM is a way of structural risk minimization technique. Then I will talk about support vector machine, the types of support vector machine, how SVM actually works. Then I will talk about like if the data are non-linearly separable, then how SVM is going to manage that. So in regarding that I will talk about kernel trick, type of kernel functions that can be used. Then finally I will conclude with the advantages and disadvantages of the support vector machine. So what is VC dimension? VC dimension is a theory that helps us to understand the capacity of a hypothesis class used by a machine learning model to classify the data point. That means it is a concept that is talking about how many possible way we can separate in number of data points. So as we can see in the right hand side picture, there are 2 points in 2-dimensional space. So what are the possibilities of this data point may be having with respect to classification? So that may be possible that the both data point belongs to class, maybe there are only 2 classes, because 2 data point they cannot be like more than 2 classes. So possibility maybe both belongs to same class, both belongs to class 1, both belongs to class 2, or maybe happen that first one belongs to class 1, second one belongs to class 2, or second one belongs to class 1, first one belongs to class 2. So if I look into this data point, there are 2 to the power, as there are 2 data points, so 2 to the power 2 possibilities are there by which I can separate these 2 data points. So there are 2 data points, there are 4 possible ways I can separate them. In the first picture, like top left, we can see that both the data points are at the maybe above the decision boundary. In the second one, I can see it is between the decision boundary, where the red circle is below, red point is below, green point is above. In the second case, the green point is below, red point is above. And in the last image, the right bottom image, where we can see that both points are below the decision boundary. So this is the concept of scatter. How many data point we can scatter? And in this case, if there are 2 points, there are 2 to the power 2 possibilities are there to scatter the data points. Now if any model, here in this example, a decision boundary, if it can scatter the data point in all possible ways, then that is called as VC dimension. So in this case, if there are 2 points, a particular line in 2D case can separate the data in all 4 possible ways. And in that case, now if in place of 2 data point, if there is 1 data point, will it be able to separate them in all possible way? If there are 1 point, then it is 2 to the power 1 and 2. So 2 possibilities are there. Either the point is above the plane or below the plane. So a line can separate them. If I consider 3 point, 2 to the power 3, 8 possibilities are there. Can a line separate them? Is it possible? You can try it by your own also. Take 3 points, and so 8 number of possibilities may be there, 2 to the power 3. Now can you draw a line which will be able to separate the data point in all possible way? So either 3 belongs to class 1, 3 belongs to class 2, 1 belongs to class 1, raised 2 belongs to class 2. So overall 8 possibilities are there from the like binary theory and all can have a point can be in a class 1 or class 2. If there are 3 point, so 2 into 2 into 2, all having 2 possibilities, so 8 possibilities are there. In that case, can I draw a line that will be able to separate the data in all possible way? Just anyone, please respond, answer. Yes, answer definitely yes or no. Can a line separate 3 points in all possible ways? Definitely no. So maximum how many point a line can separate? 2. So in that case, if I consider line as a decision boundary, obviously in this 2D case, in that case VC dimension is 2. So the maximum number of data point it can settle, that means it can separate in all possible way or classify in all possible way, is called the VC dimension of that particular classifier. In this case, the decision boundary, the classifier is a line, linear line, and that line can maximum separate 2 data point. If there are more than 2 data point, all possibilities of this distribution of the data point in classes, it cannot separate. Now, so if there are 3 data point, it cannot be settled. That means all the possibilities cannot be handled by that line, and in that case, maximum VC dimension for the classifier line is 2. If there are 4 number of data point, you can see in this example, if I consider a classifier which is whose decision boundary is a square, in that case it can separate. So if there are 4 number of data points, so how many possibilities are there? 2 to the power 4, 16. And as you can see, if I use a square, it will be able to classify all 16 possibilities. You can see all the example where each point can be either belongs to green class or the red class, and all 16 possibilities can be correctly classified by the decision boundary square. So if I use any machine learning model which generate the square decision boundary, it will be able to classify 4 data point in correct way, in all possible way. But if there are more than 4 points, it may not able to do that. So all the classifiers who draws the square decision boundary, for those classifiers maybe the VC dimension is 4. So VC dimension is talking about the capability of a classifier, and that is why it is a theory we are supposed to know. But along with this, we also come with the concept of the complexity. So in real world, the data sample may not be having all those situations, like all possibilities may be there, all complexity. So it is the maximum number of complexity a data can process. And if a classifier is going to handle all those complexities perfectly, that is the VC dimension. That is hypothetical. But if we blindly going to come up with a classifier that is able to identify every possibilities of the data distribution, sometime it may not be required or it may not be relevant. It is unnecessarily making the classifier complex. Like in the first example, there are 3 data points. Now suppose it was the case that always 2 points are lying one side of the boundary, and if it is possible that always the same class samples are in the same side of the decision boundary, in that case we should be able to come up with a classifier that draws a decision boundary and able to separate 3 data points, because these are the all possibilities. Suppose in my data set there are data samples for which always the 2 points lie on a same side of the decision boundary. So suppose the data point not having these situations. So in this case, okay. So I need to change one thing. Like you can use a line to separate all the 3 data points. You can separate, as you can see in this picture, it is perfectly possible to separate 3 data points using a line. So I would like to say that for any classifier which draws a decision boundary, if there are 3 number of points, it can correctly classify them in all possible way. So for a classifier having a linear decision boundary, like in this case a straight line, the VC dimension is 3. But if I increase for the like if the number of sample is 4, in that case a line cannot separate them. So I would like to restate my statement. So if there are 1 data point, a line can be drawn that is going to separate the all data points in all possible way. If there are 2 data points, I can draw a line, they are going to separate them in all possible way. If there are 3 data points, then also they are supposed to be separated by a line, as you can see in this image. So but if there are 4 points, it may not be able to separate them correctly, like in this example. In this like in this example, you cannot draw a line that will separate the red circles and the green circles, because always like in the XOR case, you cannot draw a line which is going to separate the data point. Because if you draw a line, in that case, this example I was talking about, no? So here if you draw a line, you cannot separate the data point in 2 classes, because if you draw a line, there will be red point in both the side of the decision boundary. So the decision boundary cannot say that if it is left it is class 1, if it is right it is class 2. It cannot do so. So if the number of data point become 4, it cannot classify all possibilities, and in that case maximum number of data point a line can separate, or a set of classifier with a linear line decision boundary is maximum 3. Now in that case, should I always use a complex classifier which having a more complex like square type of decision boundary? No. Suppose in our data, all this sample is present in my data, this sample is present in my data, this sample is present in my data, all these samples are present in my data, but suppose the data do not have this sample. So if the number of sample, because the data set which we always have in our real world, that do not represent all possibilities. They represent a few of them, or a few of these possibilities. So suppose that particular case is not present in your data. So in that case, even if there are 4 number of data points, by using a line you can separate them. Am I clear to everyone? So what I mean to say, VC dimension is strictly saying that this many number of data point, it will always be able to classify correctly. So if there are 3 data point, I can always draw a line, whatever be the data possibilities, data classification category possibilities, it will always able to do that. That is the VC dimension. But in real world, suppose some negative possibilities like here, if those case scenarios are not present, in that case a line still able to classify 4 data point. So VC dimension is like strict bound, and model is more complex, where if the 4 number of data point is there, they are asking that you have to use a square, you cannot use a line. However, in a real world, you can go with you may not need to come with the classifier with this kind of strong decision boundaries like square or complex decision boundaries. You can still go with a simpler decision boundary lines. So drawback is what? Drawback of VC dimension is it is making the decision boundary very complex, and which may good or best for the classification for those set of data, but real world data may not represent all possibilities. So may not be, we should be so strict. So understanding and calculating the VC dimension can be mathematically complex, definitely. Next is that a high VC dimension indicate high model complexity. That means the decision boundary will be complex. And in that case, which can lead to overfitting when training data size is insufficient. In practice, we balance the VC dimension with other factors like data size and the noise. So what I mean to say by these words is that if your model having low VC dimension, that means like 2 or 3, in that case your decision surface will be more smoother, more simple. But as your machine learning model is going to increase the VC dimension in its complexity, the decision surface is going to get complex. Like previous example, for 3 it was line, for 4 it becomes square. Maybe for 5, 6 or 10 dimensions, number of samples, the VC dimension is going to become more critical, and in that case the decision boundary is going to get more complex, and which may be more tuned toward the number of samples present over there. So a lower VC dimension indicate less complex model, reducing the risk of overfitting. So in that case, the more training data lead to better generalization by reducing the gap of empirical error and the true error. Now what empirical error? In any machine learning model, we first train our model with the training data, and later we test our model with the test data. Now what is the concept of overfitting? Concept of overfitting says that if your data is working pretty well with the training data and it is not performing well with the test data or unseen data, it is called overfitting. So now how we train any machine learning model? We basically check its performance. We don't know the test data. Test data will come during that evaluation. Like in an exam, whatever in a class, I can teach something, ask the student will respond. If the answer is 90% correct or wrong, in that case I can improve the answer of the student's question. I will train them, but during exam we only put the question and they have to answer, and there is no actual answer. In medical test, when we go for the testing, they give some test report, and now nowhere it is possible that is the ground truth, and there is actually no ground truth. After the test result, we know that this is the result. We don't know what is the exact true test result by which we can compare. So during testing we cannot compare, but during training we can get the result. We know the actual result. We can compare between them, and we can understand how much wrong we are. And we can keep on improving, minimizing the difference between the actual answer and the answer we have given, and we try to improvise ourselves. So during training time, improvisation is done. Testing time, it is only inferencing. Whatever you give the input, it will give an answer. But that answer, actual true answer, is not known to anyone. So that is called the true risk. True risk means the risk while we are testing. Because if I do a test or something, I got an answer. Like what will be the weather for tomorrow? What will be the temperature tomorrow? Someone may say 24 degrees Celsius. But unless we go to the next day, we don't know whether our answer is true or wrong. I made a weather forecasting AI model, ML model, that is telling me tomorrow temperature is 24 degrees Celsius. So I can ask that model, maybe I have trained my model till the 31st December 2025. I can ask the model during testing that what is the temperature for the first 31st days of January month in 2026. It will give answer. I can compare that answer with the actual temperature on those days, and I can know how much correct I am. But if I ask that model what will be the temperature for tomorrow, maybe tomorrow date is maybe 9th. So what will be the temperature on 9th of February? So until we go to the next day, we don't know whether our answer is correct or not. But that is the answer given by the model. So that is the true risk. So if I say tomorrow temperature will be 24 degrees Celsius, so whatever I say, that is a true risk. Means whatever is mistake has been done, that is not known to me. And empirical risk is there, the risk on the training data. So during training I got some error, and I keep on training myself, and after a certain time I know that I cannot improve much more than that, and we stop there, and that is called the training error, and also called the empirical risk. So in general, empirical risk or training error is always less because there is a chance of improvisation. But when we try to test with the new data that not has been used during training, the error is supposed to be little higher because for those data we have not trained. So VC dimension is talking about, it is the empirical error is always be the empirical error plus the model complexity is always higher than the true error. So what I mean to say that this is the empirical risk. Empirical risk is the training error, and training error along with the complexity of the model, that will always be less than the test error or true error. Now penalty, this the complexity of the model, that is strictly defined by the VC dimension and the number of sample. Here n is the number of sample. So as you can see, as VC dimension increases, the number of sample you are using in your training, it should keep on increasing. So if your model is very complex, many a time we may have heard those terms. If you want to use a complex model, use more training data. If your model is simple, it can work well even if the number of training sample is less. So that is the ratio. As the VC dimension keep on increasing, you are supposed to increase the capital N, which is the number of training samples. If your number of training sample is less and the VC dimension is high, the penalty will keep on increasing. But if your model is like simple and like denominator number of training sample is high, but the VC dimension model is simple, in that case penalty will be low. And in that case, even after adding that small penalty with the training error, it is going to provide you the upper bound on the test error. Now, test error should be less than certain quantity. So test error is, this is I am providing the upper bound, means how much error I can tolerate in real world. Like when I am predicting what will be the temperature of tomorrow, you can come up with the answer like 89 degrees Celsius or minus 2 degrees Celsius. So these answers are absolutely wrong, no? So I need to upper bound like how much error I can tolerate on the test scenario which is not known to me, because based on the test result I am going to make the call. Now test result is too much wrong, that is going to have a very adverse consequences. So like if I can say that if your answer is plus minus 5 degree is acceptable, but if your answer is like too absurd, I should not accept it. So that is why the true risk estimate, that means test error, need to be bounded. So when I am testing, the error should be within an acceptable range, and that range is training error plus the complexity of the model. And that is why it is suggested to keep the penalty as low as possible. So how it can be improved? Either by increasing the number of training samples N. If N is increasing, then you can see penalty will be low. If the VC dimension is low, the numerator, in that case also penalty will be low. And in that case, the upper bound on the true risk will be low. So this is the concept of structural risk minimization. I am putting the cap or upper bound on the test error. Now support vector algorithm majorly used for classification, but it is also used for regression. Classification means I need to classify a particular test sample into a category or label it. In regression, I need to, based on a set of input, I need to approximate what should be its output value, and output can be any real value. In regression, output always a real value. In classification, output always a discrete value. If there are C number of classes, so output can be from 0 to C any, 0 to C minus 1. So the objective of the support vector machine algorithm is to find the optimal hyperplane in n-dimensional space that can separate the data point in different classes in the feature space. If your data is n-dimensional, in that case I need to get a, so if the data is two-dimensional, a line or straight line should be able to separate them. If the data is 3D, you need to have a plane to separate them. So if I want to separate all those points which is in the floor and all the point which is in the ceiling of in this room, so there are a lot of in between high plane is there that is going to separate all the data point of the floor and all the data point of the ceiling. Similarly, if the data is higher dimensional, the plane need to be hyperplane. So that is what I mean to say here. I need to draw a hyperplane, that means a linear decision boundary that can separate the data points. Hyperplanes tries to maximize the margin between the closest point of the different classes, and the dimension of the hyperplane depend on the number of features. Like I said, if the features or input is two-dimensional, you can draw a line to separate them, straight line. If data is three-dimensional, then you need to have a plane to separate them, and if is higher dimensional, you need to have a hyperplane to separate them. But in all these situations, the decision boundary is always a linear. Decision boundary is not any kind of curve. Now as we can see, there are two type of SVM can be possible. The first one is linear. So linear SVM used to linearly separate the data. So in the first example, linear means you can draw a line to separate them. So as you can see, there is a line, you can separate them. So linear SVM is used to linearly separable data used for, which means if a data set can be classified into two classes by using a hyperplane. Nonlinear SVM is used for non-linearly separable data, which means the data cannot be classified using a hyperplane. So in this case, you cannot draw a line to separate them. So you need to have a like quadratic decision boundary, in this case x square plus y square, circle decision boundary to separate them. Now this is the crux of support vector machine concept. Here it is talking about maximizing. So basically SVM is the approximation of the structural risk minimization, which I said that I need to put a cap on the maximum allowed test error, which is less than training error with penalty. So maximizing the distance. So my objective is to maximizing the distance of the decision boundary from training point minimizes the VC dimension, resulting in good generalization. By these words, what do I mean? By this word, I mean to say, suppose there are two classes. Now, one are blue, these samples are blue squares. These samples are green circles. Now, there, as you can see, there are a lot of the lines can be drawn. You can draw this line, this line, this line, all are able to, or I can draw some lines like this also, any possible lines can be drawn that are going to separate the data points into different classes. Now among all those infinite possible lines, which line I should go for? I should go for a line that having the maximum difference from the closest sample of the opposite classes. So for this line, which one is the closest sample? This one. For this class, which one is the closest sample? This one. Am I right? So this line should be farthest away from these 2 points of the different classes. That is the condition of support vector machine. And if you can increase this distance between the data point of different classes and with the decision boundary, you are minimizing VC dimension. And earlier I have shown in SRM, structural risk minimization, that if the VC dimension is low, it leads to good generalization. If I consider same number of training pattern to train the model. If I put in the denominator constant, in that case, if VC dimension is low, the overall risk will be low. So the margin, what is this margin? This is the difference between the hyperplane, this is the hyperplane, I am talking about linear SVM, and the closest data point from either class. So this is the data point for the blue class closest to the hyperplane, and this is the green circle data point which is the closest from this decision hyperplane, and this is the difference between these two is the margin. So the margin is the distance between hyperplane and the closest point from either class. SVM aims to maximize this margin, leading to more robust classifier. I could have drawn a line like this, I could have drawn a line like this, but it will not the farthest from both classes. It may be, the distance may be higher in this case, but distance will be lower in this case. So that line should be maximum distance or in between the two classes. So support, now what is the support vectors? Now for drawing this hyperplane, will this point have any influence? Will these points have any influence on drawing this decision boundary? The simple answer is no. So all the training data point will not participate in forming the orientation of the hyperplane. Only those points which are closest to the decision boundary will participate in designing or orientation of the decision boundary, and they are supporting to form the decision boundary, and due to those reasons those data points are called supporting vectors, or to be more precise, support vectors. So support vectors are the data points that lie closest to the hyperplane. So this data point, so these data points that lie closest to the hyperplane, position of this data point is critical as they directly influence the position, means whether it will lie here, here. So position as well as orientation. So whether it will lie like tilted, whether it will be like this, whether it will be like this. So the orientation and the position both are directly influenced by those closest data points and not the other data points. So that is why they are the support vectors. Now every point in vector space is a vector to as you can see, these all data points are actually vectors. Now every data point is a vector in d-dimensional space. So this data point or these vectors are supporting the hyperplane, and this is the crux of support vector machine. So up to this point, is there any doubt? If there is any doubt, I can pause a few minutes and like try to resolve if any query is there. Can you rephrase the question in a different way? Okay, that will come end of the day. What I get? Okay, so if I would like to answer the question, let us start with the vector concept. As you told matrix, I should come up with a vector concept. So in this example, data is simply two-dimensional. So it will be a column vector. So column vector, the value with respect to x1 axis, value with respect to x2 axis, it will be column vector. And the line is a straight line, so I can say it is y is equal to mx plus c. Y is equation of a straight line, y is equal to mx plus c. So in that case, what I need to know that for all these data points, which is a column vector, I need to check whether the value of that column vector is greater than that equation value. I will put like y is equal to mx plus c. So m is slope, c is intercept, and x. So what in general we do, we put the x value into the equation and check whether the value is positive or negative, and based on we decide whether it is on the left side of the decision boundary or right side of the decision boundary, isn't it? And if the value is 0, then that point lies on the straight line. No, I'm not going that. I am going to explain. What I mean to say that how do we classify the data point? So we basically, this is the hyperplane is simply the equation of a straight line, y is equal to mx plus c. You put the value of x. If you get a negative value, it in left side. If it is in positive value, you got on right side. If the value is 0, you got it is on the line. That is what we get to know. Now the question is how we decide the orientation of the, like whether it will be tilted like this or this or this, or it will be here or here or here. That decided by the vectors closest to that hyperplane, that I am going to demonstrate, because that will be a optimization problem, because I told earlier that line is supposed to be farthest away from both the neighbors. So if I go by your question, so in this example, what I need to know, I need to maximize this distance. So I need to maximize the distance from this data point to this line. What is the shortest maximum distance from this data point to this line mathematically? Huh? If I ask this question to the audience, what is the shortest line between a data point and a line? Perpendicular distance. So it is the line of the equation like mx plus c by what? The orthogonal vector, na? So this is the difference. So if I say the slope is m, then m is the distance. Similarly, in this case also it will happen like this. So if you go by that, so basically earlier I was talking about this. I am going to come up with your answer. So suppose this is the equation of the line y is equal to mx plus c, or suppose I am writing wx minus b. So this is the line of the equation. If any point lies over there, it will have a zero value, and these are the support vectors 1, 2 and 3. So they are on the left side or right side of the decision surface. And now from this point I need to draw a line between the hyperplane and the support vector. Here also I need to draw a perpendicular line between the equation of the line and the perpendicular. So basically it separates the data point in two classes, positive or negative. It uses a linear decision boundary hyperplane divided the class. The goal is to find the hyperplane that maximizes the difference between the closest data point of each class or support vectors. This is called the maximum margin classifier or hard margin classifier. So suppose in this example data are x, and x may be two-dimensional vector having value x1 and x2, and y is either like label 1 or label 2. So y is particular discrete label 0 and 1, and in that case I need to get what? I need to make a separation decision boundary. That means mathematically write wt transpose x plus b equal to 0, such that if for any x, if it is positive, it will be labeled as class 1. If it is negative, it will be labeled at class 0. Up to this point I am going to answer that question, but up to this point, is it clear to everyone? Okay. So in this equation, can I multiply this into this? And so this is the like fx, y is equal to fx, and this is actually the fx. Now if fx is positive, it will be plus 1. If fx is negative, it will be negative. So what I am now going to do, I am going to multiply this with the y value. So I am going to write y into fx. So if I multiply this into this, outcome will be positive or negative? Positive. And if I multiply this into this, outcome will be positive or negative? This into this? Why negative? This is already negative quantity, na, less than 0. So again negative into negative will become positive. So both cases, so I can combine these two equations and write it simply like this. See, in the first expression, suppose it was for if it is greater equal to, I should have said, like I could have ignored it. Huh? It should be either case, like if it is greater equal to, it should be only less than. So in that case, if you multiply this and this, you are going to get plus 1. If you multiply this into this, in that case also you are going to get plus 1 only. Because positive into positive, positive, and negative into negative is also positive. So that is why if you combine these two equations, you will come up with the expression like yi, means I is the ith sample, yi into w transpose xi plus b, that multiplication will always be greater than 1. So the objective is to find a hyperplane b and w with maximal separation between it and the closest data point while satisfying the above constraint. So I need to, in this, what happened? So in this equation, x we cannot control, y we cannot control. They are data points, they are given to us. So how we are going to orient that line? That need to be farthest away from both the closest neighbors of the different classes. That condition has been given to me, and accordingly I have to draw the hyperplane. So if I form it with a mathematical optimization problem, so basically the perpendicular distance d of a data point x from the margin is given by this. So the distance is like wx plus b divided by the w, where w is the slope. So basically this is the perpendicular distance of any point or any vector from the hyperplane. This is simple math. This is the shortest distance between a point and a line. Huh? No, cardinal function not I am talking about. I am talking about simple math. The distance between a line and a data point. Shortest distance between a line and data point. Have I talked about it? No, still not. I have not discussed. So that will come later. Currently, let us stick with simple maths. So up to this point, is it clear? Like anyone having a doubt? Like this is a simple distance between a data point and a line. So in a math, we ask to compute the shortest distance between a point and a line. So we draw a perpendicular distance is the shortest distance, and this is the simple math equation for computing this. So obviously now this is what? This is actually L2 norm, two pipes are there. This is the L2 norm W. So basically in a vector space we like to write it like W transpose W. This is a dot product. So W is a column vector. If I transpose it, it will become a row vector. And with the row vector, if I multiply column vector, we are going to get a scalar value. So basically, it is going to give you a W square value. Like for simplicity, let me talk about like W can be having a two value like W1, W2. So this is a column vector. So what will be shape? If W is a column vector where there in a single column, first row there is a value W1, second row there is a value W2. So what is the shape of this? W shape is 2 by 1 na? There is a column. So in a matrix, the first row represents the first index and the column represents the second index. So if I draw a column where two rows are there and a single column is there, so first index is 2, there are two rows and there is a single column, so 2 into 1. So if I take a transpose of it, it will become 1 into 2. So if it is 1 into 2 and it is 2 into 1, so matrix multiplication is possible. The column of the first vector matrix is equal to the row of the second matrix. So 1 into 2 into 2 into 1 is going to give you 1 into 1. So basically always dot product give us a scalar value. In this case, all this case I am not going to talk about, but in this case it is going to give you a scalar value. And now this distance, when this distance will be maximum, when this W square value will be minimum, because denominator jitna much denominator will become low, the D will be keep on increasing, isn't it? Simple math. So if I can decrease the denominator, it will increase. So my objective now comes down to I need to minimize the W square. If I can minimize W square, it will automatically maximize the distance. So now overall problem of drawing the decision boundary is become an optimization problem, where my objective is to optimize or minimize W square. So to maximize this distance, we can minimize the square of the denominator, and this leads to a quadratic programming problem. Quadratic why? Because W square. So it is not linear, it is not W, it is W square. So it is a quadratic problem. Now we have to minimize. Now for mathematical simplicity, as we, in any optimization problem, we need to take the first order differentiation. That need to become 0, and the second order differentiation, if it is positive, then it was a minima. If the second order derivative is negative, it was a maxima, isn't it? Simple math. So as I have to take the derivative, first order derivative of this, so obviously square will come down, and it will make things complex, like it will become 2w. To tackle that issue, we always use half before any square term. So we need to, because end of the day in mathematical computation, it is not going to hamper any concept. So our objective is to minimizing half of w square, and this is subject to, now I cannot blindly minimize w. I need to also take care that yi w transpose xi plus b must be greater than 0 for all I. For all the data sample, this was the initial condition. Na? For if I put a data sample xi yi, this equation should always give a positive value. So this is not just an optimization problem. This is a constrained optimization problem. I cannot blindly keep on minimizing this w square value. In that case, you will say when the w will become 0, it will have a minimum value. 0 square is 0. Any direction, w is keep on increasing. So I cannot blindly minimize w value. I have to constrain by this. So now it is actually a constraint optimization problem. Now how to solve a constraint optimization problem? Normal optimization problem solving is quite easy. We take the difference. So here the two parameters are there. Na? One is w, another one is b. xi and yi are the inputs. They are not parameters. That we cannot train. But the parameter is w and I, that is going to train my model. And that is going to decide how the orientation and the position of the hyperplane will be. Now in this case, to optimize anything, we need to take the differentiation with respect to w, make it 0. So if this is the error, so I need to take del E by del w, make it 0. We are going to get an optimal value of w. If I take the first order derivation of this equation, if I derive with respect to w and make it 0, that is the minimal point. And if I solve this equation, I am going to get a value of w. And similarly, if I take a differentiation with respect to b and make it 0, means del E by del v equal to 0, then also we are going to get the optimal value of b. So that is what we do in optimization problem. But the here problem is, this is not a simple optimization problem. This is a constraint optimization problem. And for constraint optimization problem, we need to consider the subject to constraint. The constraint which is given there, yi w transpose xi plus b greater equal to 0. That inequality constraint, that need to be put into the equation. And then only we can optimize. Now for that, what we use? We use Lagrange multiplier. So we are going to use a Lagrange multiplier, and we are going to convert into a, because you cannot apply a differentiation over there directly. You need to convert into a mathematical equation, a linear equality expression you need to represent. This is inequality. So you have to represent in a mathematical equality formation, and after that only you can take the first order derivative with respect to the parameters b and w. So for that we need to use Lagrange multiplier. So to solve the above quadratic programming problem with inequality constraint, we can use the method of Lagrange multiplier. So I am applying a multiplier, mostly denoted by the notation alpha, and now the representation will look like this. So this was the minimization problem, half of w square minus sum over of I equal to 1 to m. So assume there are m number of data points. So sum over of I equal to 1 to m alpha I, this is, you can see if I go back to the previous slide, I can take this one this side, so it will become minus 1, isn't it? It will become minus 1 and it will be greater equal to 0. So I put that. So this is the expression yi w transpose xi plus b minus 1, and that whole expression is multiplied by a Lagrange multiplier alpha I, and I is the n is the number of sample. Now there is another catch. I is actually okay, you can write I, but we get to know that there are certain data point for which alpha will become 0. So those data here for this computation I am considering all the data points, all the training data points. But if for any data point alpha I becomes 0, will that data point having any influence on this decision? Suppose there are n number of data points. In this equation I am considering all the m data points. Now for any I, if alpha is 0, will that ith sample having any influence? No. So those data points for which alpha is having a value, that will contribute to this optimization equation. Other is not going to contribute. So those alpha I means those I, the training sample for which alpha is a quantity, non-zero quantity, those are the support vectors. And for those i's for which alpha equal to 0, they are not contributing into this equation and they are non-support vectors. So there I am putting the condition that this alpha I, this for some number of i's, this will become 0 and this whole part will become 0. So they will not take part in decision making. But for those cases where alpha is having non-zero value, they are taking part in the decision making. So for those i's where alpha is non-zero, they are the support vectors. Now, okay, let us go forward. Let us go forward and try to, now we get the optimization equation. This is a simple mathematical equation which we can differentiate with respect to b and w. We can make it 0 and we are going to get an expression. So this was my equation. Now just tell me if so we set the derivative of the Lagrangian with respect to w and b and set to 0, like this is L means loss, the total loss. And now earlier there was two parameter w and b. Now I added one more parameter, Lagrange multiplier. So now the equation having three parameter, w, b and the alpha. Alpha is the Lagrange parameter or Lagrange multiplier to be more precise. Now in this case, if you differentiate this equation with respect to w, what will come? It will become, if I differentiate with respect to this, w square, what is the differentiation of w square? 2w, 2w half will be cut, so it will be only w. And in this expression, if I break it like it is alpha I, yi, w transpose xi, and where if I differentiate with respect to w, it will be simply alpha I, yi, xi. And this term alpha I, b, it is a constant 0, and this is again minus 1 will be 0. This is constant. So in that and it will be applicable for all the I 1 to m. So it is a minus sum over of I equal to 1 to m alpha I, yi, xi. Is it clear to everyone? Similarly, in the second expression, if I differentiate with respect to beta b, in that case this term is a constant, it will become 0, and only term remains alpha I, yi, b, because this term will again become 0, alpha I, yi, w transpose xi, there is no b, so it is constant, and this term is also like alpha I only is also constant, so it will cancel out. So del loss by del b is minus sum over of I equal to 1 to m alpha I, yi. So I got two equations, equation 4 and the equation 5. So Now are we all in the same position? We got it, no? Now let us move forward. Now what I can do, as you can see, I know the value of W. So is it possible that I can put the value of W in this equation? Then the equation will not have any W. The equation having, so in this particular equation, I know the value of W, where it will be minimum. So I can put this value of W in this equation. Can I? Are all with me? Are you all with me? So in this was my expression. I just simplified, break it, and every time writing I equal to 1 to m is hectic, so I am ignoring it, huh? But assume it is applied over all the training samples. Now in this case, I just put the value of W in, I just replace the value of W with the value like it was alpha I, yi, xi. So in this expression, as you can see, the equation will become simply like this. This was the term W transpose W. W transpose W, if you solve it, okay, so this is going to comes like this. So expanding equation 1, if you expand the equation 1, this was my equation 1. In that equation, I am just multiplying alpha I, yi, so it will be alpha I, yi, w, xi, and it will be sum over of alpha I, yi, b. And finally, there is a sum over of alpha I. Now I am putting 5 and 6. So 5 was the value of w, which is sum over of alpha I, yi, xi. So if you put that value in this equation, it will look like alpha I, and here just to like change it because I cannot use I both the times because both are representing different indices. So I have written alpha I, y, alpha j, yi, yj, xi, xj minus this b sum over of alpha I, yi. This sum over of b you can take out outside because b is a common factor. And it is not depending on the I, so you can take b out, and this is the sum over of again alpha I, which I have written in this side. Is it okay? Okay. Now in this above equation, you may also know that this term is 0. In the previous equation, we get to know the sum over of alpha I and yi equal to 0 from the first order loss with respect to b. So this term is 0. So in this equation, I make this term, in this equation I make this term 0. So it will simply this expression, which only having alpha I. So overall optimization problem can be represented with a single parameter alpha I, which is a Lagrange multiplier. Up to this, is it clear to everyone? We have ample time, we can go very slowly. Okay. Now this problem is called the initial equation with the Lagrange multiplier, that was the primer equation, or we used to call a primer problem. But now we have converted this equation with respect to only Lagrange multiplier, and now this problem is called the dual problem, because if we know the alpha value, we can derive the W value, isn't it? If I go to that equation 5, if we know the value of alpha, we can get the value of W, as you can see in the equation 5. So this is the dual problem in support vector machine, where if we know the alpha, we can recover the W, but not vice versa, huh? Like in this equation, as you can see, if you know the alpha, you can know W, but if you know W, you cannot identify individual alpha. So it is not vice versa, and that is the core concept of the primer problem and the dual problem. now this is like this is some assumption type of writing I have put it here. So this is somehow B needs to be with respect to positive sample and negative samples, but overall classification I would like to focus on, like W should be obviously sum over of all the samples alpha I, yi, xi, and B, if you sort it out, it will look like this: B equal to half of all those cases where these are positive samples, yi is positive, all these cases where sample is negative, and if you can take the minimum of this sample, max of these samples, you somehow are going to get the value of B. So I am not going into that detail. So end of the day, this was my expression. Now suppose a new sample, so I equal to 1 to n, those were the training samples. Now I am going to talk about a new sample. Sample may be Z. Z is a new sample, and that sample I would like to classify. And in that case, I will put this particular sample into this equation, and if that equation gives a overall expression is positive, that Z sample belongs to positive class. If it is negative, the Z sample belongs to negative class. Because this was our earlier expression. Now, if we can go back, you can see this is what our equation was. Sum over of alpha I minus half of sum over of m ij, and this was the expression. Now here, if I would like to solve it with respect to Z, so initial equation was like this. The first one, this was the equation. So here this was the equation where in this place I am going to put the Zi. So if you put here the Zi, you are going to get either positive value or negative value, and based on that you are going to classify. Now dual problem, like I was talking about. So basically end of the day we need to solve this problem, and this problem is subject to alpha I positive. So properties of alpha I when we introduce Lagrange multiplier. So basically the alpha I in the Lagrange multiplier is always a positive quantity or zero. It cannot be negative. Means for the sake of saying alpha I is supposed to give me a positive value, but it can give a negative value, but we are considering that it is supposed to be a positive value, and sum over of this is always zero. From the first order derivative of the B we got to know. So in this case, this is the dual problem. Like I told earlier, if you know all the alpha, you can recover W, but if you know W, you cannot individually identify alphas. And the initial problem was primal problem. This is the dual problem. So it has been observed that now it is a common optimization problem with a single parameter alpha I. A global maximum alpha I can always be found. That means you are always going to get a alpha I that is going to maximize this function. Okay, here I would like to point one more thing. The primal problem was a minimization problem, no? The primal problem was a minimization problem. We needed to minimize the value of W square subject to that condition. Now the dual problem is not a minimization problem. Primal problem was a minimization problem where our objective is to minimize W square with respect to certain condition, subject to certain condition. However, dual problem, as we need to get alpha I, and alpha we always need to maximize. We need to get how many positive alphas are there or non-zero alphas are there. So primal problem was a minimization problem, and the dual problem now become the maximization problem, and where we need to get the maximum out of it, not the minimum out of it. That is the distinction between the primal problem and the dual problem. We can consider from the point of view earlier, we were in a primal problem, we would like to draw a decision boundary, and that decision boundary should be as low as possible. That was the primal problem. But when we look at the problem from the point of view of the discriminator, suppose, let me explain with the example. Suppose there are two chairs is there, chair 1 and there is another chair, chair 2. So my earlier objective is to check that if the W is less, then chair are further away. Now I am want to look from the midpoint. I wish to know that how far the closest point of the two different classes are. So now I am looking from the midpoint and I would like to make the point as much distance as possible from my center point. So now dual problem is a maximization problem. And this is you can always get a value of alpha I, and those alpha I for which they are having some value non-zero, they are the support vectors. So this is the math behind support vector machine. So many of the alpha is a 0. So W is a linear combination of small number of data points. As you can see, there is no square term, no? So this is a linear combination of the data points, as simple as that. So for those data point alpha is 0, those data point is not contributing in W, and for those data point where alpha is non-zero, they are contributing to the value of W, and W is a slope, so it is taking care of the orientation of the decision. So orientation of the decision surface will always be influenced by the alpha I which are non-zero, or those vectors which. So basically, if I would like to more elaborate this fact, so in this expression we can see if alpha I is 0, that particular xi having no influence, or that particular training sample having no influence. But if alpha I is positive, then corresponding xi will have influence on computing the value of W. Now each alpha I will have not same weightage. So we can consider it as a weightage system. So if alpha is low, that corresponding xi will have low influence on the W. And if the alpha is very high, that corresponding xi will have a high influence on the W. So W is a linear combination of small number of data points. This sparse representation can be viewed as data compression, as in the construction of KNN classifier and all. So what I mean to say that only few data sample is going to take part in the orientation and the position of the decision boundary, and most of the point will have no influence on the decision boundary. So xi with non-zero alpha I are called support vectors, like I told many times before. The decision boundary is determined